SwayamPrabha. Digital India. Educated India.
Welcome friends, we will move on to lecture 2. So lecture 1 we had a very basic introduction on composites, different types of composites. So today our prime focus will be towards matrices. So in today's lecture we will see matrices, the characteristics of matrices, functions of matrices, different types of matrices, and here we are more focused towards polymer matrix composite. So we will see different types of matrices, that is thermoplastic matrices and thermoset polymer matrix composites. A rewind or recap of last class: you have to make a composite, you need 2 or more ingredients. The most predominant ingredient will be matrice, it will be called as matrice, and the reinforcing agent will be those which give strength to the composites. So matrix can be of any type, it can be made out of polymer, it can be made out of metal, or it can be ceramic. The reinforcement, like discussed last class, it can be continuous, it can be discontinuous, it can be particulate type. So depending upon these 2 combinations, we would always try to have a synergetic output as a composite material. So if I try to go a little bit about composites, for example, if you want to make a thick, or if you want to make a part wherein which it has all 3 dimensions. So if you look at it, this is what is a composite. So the composite can be made out of bulk as one, and they can have 3-dimensional reinforcement, or they can be stack of several layers to form a 3D composite. When it is several layers stacked, it is called as a laminate, and one layer is called as a laminate. So in a laminate we will have a reinforcing agent and we will have a matrix. So that is nothing but a layer. So in a layer what you will have? You will have reinforcement as well as matrix. So if you look at it further going backwards, the polymer is nothing but a repetitive unit cycle of polymers is reinforced with a reinforcing agent, and several of them stacked together forms a composite. And you can see there are circles with smaller circles and larger circles. So this shows very clearly that you can keep changing the orientations of the layer to get the required output. So that laying of different layers is called a stacking sequence. The configuration of a laminate that defines by ply composition and the exact sequence of ply orientation and its thickness is called as a stacking sequence. So when you discuss about matrices, and I told very clearly that we are more focused towards polymer matrix composite. So polymer can be classified into 2. One is called as plastics and another one is called as elastomers. And plastics can be further classified into thermoset and thermoplastic composite. Very crude differences. It is non-recyclable and this is recyclable. Thermoplastic can be further classified into commodity plastics, engineering plastics and high performance plastics. Commodity plastics are plastics wherein which there is not much of load component, and it is predominantly used for household applications or for some entertainment. For example, making a closure for a machine tool is called as commodity plastic, wherein which it does not take any load, it is a secondary structure. The next one is engineering plastics, wherein which it has high strength and it also is taken to a place or to a service condition where there is temperature involved. High performance plastics are for endurance cycle, all these things we can look at these type of plastics. When you go to elastomers, the difference between thermoplastic and elastomer is the ductility. So here it can go up to 1000%, depending upon the combination, playing with the properties. Elastomer can go up to 1000% ductility. So you can have, this is classified into two. One is called as natural, the other one is called as synthetic. Since there is lot of components coming out of elastomers today, so people are more and more moving towards synthetic elastomers. Natural elastomers, again there are two classifications, one is latex, another one is vulcanized. When you talk about synthetic, again you can divide into two, which is called as thermoset elastomers and thermoplastic elastomers. Moving further, when you try to see the molecular arrangement of inside a polymer, it can be like this. People call this as Kinkini structure, where in which it is like a coiled spaghetti. You can keep pulling one thread and it stretches itself. So these are called as amorphous structure. Amorphous polymers are those polymers where in which it is not arranged in a uniform or a periodic pattern, and it helps in mobility of the chain. So these are amorphous polymer. And there is another classification called as semi-crystalline polymer, wherein which there is some zone wherein which a fixed arrangement pattern is seen, and in some places there is a randomness there. Is there a crystalline polymer? No, 100% crystalline polymers are not available, or it cannot be made. The polymers can be of two classification. It can be amorphous or it can be semi-crystalline polymers. Depending upon the amorphous, their properties like transparent, translucent properties, all these things changes. So before getting into understanding the thermoplastic and thermoset matrices, let us first try to understand what is a function of a matrix. Let me go back to this figure which we discussed earlier. So in this figure, you see that it takes a broad base. It is like a broad base, and in that broad base, this reinforcing is pushed inside. So what can be the function of a matrix? So the first thing is it helps in holding the matrix. Second thing is it helps in protecting the matrix. The third thing is it helps in distributing the load on the reinforcement. The last thing is, if you want to selectively make the reinforcement to take the load, that work also matrix can do. This is what it is. So now let us go ahead and see the functions. Whatever I have said and whatever we could guess is written here. First thing is, the matrix material binds the fiber together and makes sure the load is uniformly transferred across the fiber. It provides shape and rigidity. If you have only reinforcement, we cannot make a product. So in order to make a product, we try to use matrix and a reinforcing agent. So it provides rigidity and it provides shape to the structure. Second thing, as I told earlier, if you want to selectively make the fibers to take the load, that is possible by properly making the matrix, and the matrix is allowed to isolate also fibers so that you can make sure those things take over. Second thing is it tries to protect from the service environment, or I can put it this way, suppose if there is a crack which is keep growing and the matrix makes sure that it diverts a crack, and so that the energy is dissipated, the crack's progression gets prolonged and the service life enhances. So it is one of the major property or a major function of a matrix to make sure that it makes the crack growth slower. Then it gives you a good surface finish. As I told you earlier, it also helps in making near net shape. So when you talk about matrices, three types I have already discussed. Now let us get into different examples of thermoset polymer and thermoplastic polymer. So under thermoset, you have epoxies, which principally is used in aerospace industry, marine industry, transportation industry. Everywhere it is exhaustively used. So this helps in ease towards manufacturing. Then you have unsaturated polyester and vinyl ester. They are commonly used in automotive, marine and chemical and electrical appliance. You have phenolic resin, which is used for bulk molding components. That means to say thick components. You have polyimides, which is for high temperature aerospace application, which can vary from 250 degrees Celsius to 400. That is what is the typical temperature we are working on. It is not that thermosets are always room temperature, slightly higher temperatures also played around. When you talk about thermoplastic, the different examples are different aliphatic groups, wherein which aliphatic polyamides, you have polyester, polycarbonate, polyacetate. Polycarbonates are exhaustively used in rapid manufacturing. That means to say in FDM process, we use polycarbonate as a wire, one of the wires for processing it. So polycarbonates. So these are predominantly used for used for injection molding process, wherein which you will not have continuous fibers. When we talk about manufacturing, we will talk about what happens with continuous fibers and what happens with discontinuous fibers. So kindly make a note here that aliphatic polyamides, polyester, polycarbonates and polyacetate are used for discontinuous fiber reinforcement through injection molding process. You also have aromatic polyamides, you have PEEK, polysulfono, and then you also have PPS, PEI. All these things are used for high temperature applications. Now let us see the difference between thermoset and thermoplast. As you all know, thermoset non-recyclable, thermoplast recyclable. Biggest difference. The next difference is when you are trying to process, it is always easy to use thermoset because it does not have very high viscosity. So if it can exist in liquid form, it can exist in solid, which we can quickly convert into a liquid form. So the viscosity is not very high. So if the viscosity is not very high, then it can quickly flow around a confined path or flow around the reinforcement to make a product. Whereas thermoplastic is concerned, when you try to take it to a high temperature, it becomes viscous. This viscosity is very high. You always need a pressure as a one more aiding parameter to make sure it flows through the confined path or around the reinforcement. So the temperature and pressure requirements are very less as far as thermoset is concerned, but in thermoplastic these pressures and temperatures required are very high. Thermoset has unlimited storage life or shelf life. That means to say you buy a resin, it has a validity for 2 years. Whereas a thermoplast liquid form is very difficult. When you are trying to make composites solid to liquid, that means to say high viscous liquid, it does not have a larger storage life. The post curing, one thing you should understand, the polymer, when you make a polymer matrix composite, 100% setting never happens. The setting happens up to 95 to 96%, and over a period of time all these cross linkings happen and small changes happen within the polymer, and it becomes 100% cure after a long period of time. As far as thermoset is concerned, we don't need to use the post curing often necessary for optimizing. So here as far as thermoplastic is concerned, post mold treatment is not recommended. So here you try to get the full part, near net part as in one shot. But the biggest problem is in thermoplastic the shrinkages are very high. So you have to make sure in your mold design itself these properties are taken care. So it has a very high strength to modulus thermoset. The toughness and very less brittleness is there. It has low tensile elongation. It has relatively high tensile elongation. When you talk about thermal stability and chemical resistance, thermoset is good as compared to that of thermoplast. So it has very low creep resistance. It has very high creep resistance. Predominantly it is amorphous. It is semi-crystalline in nature. The post formability is not possible as far as thermoset is concerned because it is not recyclable. So here it is still doable. So it is very difficult to repair. Here you can do some amount of repair because it is recyclable. So the recycle is difficult and the recycle is very easy as far as thermoplastic is concerned. So here are some of the properties, various properties which we have compared. So you can see here the first one is modulus with respect to temperature. So here since it is a polymer, it does not have a exact point of transition from solid to liquid. It gets into a zone and then it gets converted into a liquid form. So this is called as glass transition temperature. So you can see that the modulus falls drastically down after the glass transition temperature. So the crystallinity, you remember we discussed about amorphous and crystalline. Moment you start increasing the crystallinity of the polymer, you can see there is an enhancement in the modulus. That means to say semi-crystalline material will have higher properties at higher temperatures also. So here you can see that modulus increases with respect to temperature here by changing the cross-linking. That means to say as and when I increase the cross-linking density, that means to say number of cross-links present in a unit area. If I can keep on increasing, then you can see the modulus remains almost constant for varying temperature. Okay. So here in this slide we have seen the variation of tensile modulus with respect to temperature. Why am I talking about temperature? Because temperature is one major parameter which is used while processing polymer composites. So that is why we are trying to put here. So this shows an amorphous thermoplastic, this shows semi-crystalline thermoplastic, and this shows a thermoset of a polymer. So this graph clearly says that the involvement or the influence of modulus on temperature is clearly shown here. So crystallinity is very important, and the glass transition temperature is also very important. You have to record the glass transition temperature for a polymer such that this data is useful while processing a polymer matrix composites. So here you can see, depending upon the loading rate, a stress versus strain curve, loading rate. See, for example, you take a small rubber band which is made out of an elastomer material. You pull it at a very high strain rates, it fractures. If you slowly pull it, if the strain rates are very slow, you can keep elongating it for a longer time. So this is what we are trying to show in this graph. This property is very important because this property tries to decide how the load gets distributed in the composite and what should be done. So you take here, this is stress, this is strain. Okay. So stress versus strain graph. So here let us take the influence of loading rate. The loading rate pattern increases, that means to say at higher loading rate, the ductility falls down drastically. The E enhances drastically, the Young's modulus. As the temperature goes higher and higher and higher, the polymer gets softened. So because of this softening, the strain rates, the strain is going for a longer time as compared to that of the stress. This graph clearly says if you want to process a polymer matrix composite, or if you want to process a thermoplastic material, you should take it to a higher temperature such that you bring in ductility. Moment ductility is brought in, the shape to which it is manufactured can be achieved easily. So now let us see the different polymers, different sets of the different thermoset resins, and then we will see some of their properties so that you will understand which one to choose for what application. So under thermoset resin, we have polyester resin, we have epoxy resin, we have polyimide resin, and we have phenolic resin. The most common resin is polyester resin because it is very, very inexpensive, or it is very economical. Polyester are low cost resin systems and have often excellent corrosion resistance. These composites are used, thermoset composites are used for making bridges, making containers wherein which water is carried or some acid is carried. So they always make through polyester resin because of its economic nature, and it is always available in a liquid form. So liquid is easy to give a shape. So the operating surface temperature for these polyesters are very low as compared to that of the epoxy. Room temperature itself you can make this composite. The resin contains a number of C double bond. When you talk about a polymer, it is only C and H with all other bonds. So it is C double bonds are there through which the cross linking are established. So what is cross-linking? Suppose let's assume you have a chain, a polymer chain, and then you have another polymer chain. So between these two chains, let's have you have secondary bonds. These secondary bonds, if they try to lock all these bonds, then what happens? The mobility of this chain is not available. So moment the mobility is not available, then the polymer becomes stiff. That means to say it is cured, cross-linked, and it is cured. So the strength of the polymer enhances. So the resin contains a number of C-double bonds through which cross-linking are established. Moment cross-linking established, it is cured, plus the strength property enhances. And ester, polyester. So ester is a product reaction between an acid and an alcohol. Similarly, unsaturated polyester resin is produced by reacting unsaturated acid / anhydride with a dihydric alcohol. This is how the polyesters are made. The saturated acids are added to modify the chemical structure between the cross-linking sites. The dilutant also contains C-double bond through which the cross-linking are established between the neighboring polyester molecular chain, thereby making it stronger. So this is how a polyester is manufactured, and this is how a manufactured polymer is cross-linked and the strength enhances. So if you look at this graph, it clearly says the effect of saturated acid to unsaturated acid ratio on the properties of thermoset polyester resin. So you can see this is the heat deflection temperature curve with respect to the ratio. This unsaturation and saturation acid tries to talk about the cross-linking density. So you can see that as the ratio increases, the tensile strength increases. The tensile elongation increases. You can see that this is percentage of deflection and this is tensile strength. So polyester resin, the effect of increasing styrene content on the properties of the thermoset polyester resin, you can see that the molar ratio of styrene to polyester unsaturation, you can see what happens to the HDT curve and the tensile properties and tensile modulus. You can just compare it with the previous graph. Here the graph, how does it behave with respect to saturation and unsaturation, here with respect to styrene content and the polyester unsaturation. Next, let us move on to epoxy resin. Epoxy resin is the next most commonly used thermoset resin. So epoxy is very versatile resin system. It allows for a broad range of properties and processing capabilities. It exhibits very low shrinkage. Low shrinkage is very important because in a liquid form, when you try to use a resin and when the resin gets cured, that means to say when it is completely liquid is converted into solid, the shrinkage, if it is very less, then the shape whatever you want, you can easily get it done. If there is a shrinkage, then this can be happening three-dimensionally and it is little difficult to control the output. But as far as epoxy, since the shrinkage is very low, it gives excellent adhesion with various substrates and it gives very high strength. Epoxy are most widely used in resin matrix and is used in many applications from aerospace to sports. There are varying grades of epoxy with varying level of performance to meet different applications. The epoxy, just by tweaking small percentage or just by changing amorphousness to semi-crystallinity, so you try to get new properties. The epoxy resin has the advantage over all other thermoset resins. These are so it is the absence of volatile material during curing is one of the biggest thing. It has low curing shrinkage. It has excellent resistance to chemical and solvent. It has excellent adhesion to wide variety of fillers, fibers and other substrate. See, it is very important property. If you don't have a good wettability property, then matrix and resin will not get locked and you will really not be able to enjoy the advantage of a composite material. the enjoyment of the composite material comes if you have a proper link or proper bonding between the polymer and the reinforcing agent. Epoxy gives that in a big way. So that is why epoxy resins are exhaustively used under thermoset category for various polymer matrix manufacturing. Next, let's move to polyamide resins. The polyamide resins work on slightly higher temperatures. So where the polymer requires high service conditions, so we always go for polyamide resins, are high temperature polymers which can be used up to 230 degrees Celsius for a longer period of time, and it can also work up to 300 for a shorter period of time. The polymer contains OC N/OC group, which are polyimides. Imides are classified as thermoplastic polyimides and thermosetting polyimides. The thermoplastic polyimides are derived from condensation reaction between an anhydride or an anhydride derivatives and diamides. Thermosetting polyimides are derived by addition reaction between unsaturated group and of an amide monomer or an oligomer. So this, you should have this in mind. Polyimide can exist in thermoplastic form as well as in thermosetting form. One is done by condensation, one is done by addition. So in the last class, previous lecture, we discussed about what is a addition reaction and what is a condensation reaction. So please keep that in mind. Polyimide, high temperature application, and it can exist in thermoplastic polyimide as well as thermoset polyimide. Next is phenolic resin. Phenolic met FAA and jar requirements for low smoke and toxicity. So the smoke content which gets evolved or the toxicity which is getting evolved as far as phenolic resin was very less. So FAA is an agency. They are used for aircraft interior, because you should understand, in an aircraft internally, if there is a by accident, if there is a smoke getting evolved, if there is lot of smoke, it chokes the passenger. So they try to use phenolic resin because it does not generate smoke. Okay, it is stove bins, galley walls, as well as other commercial markets that require low cost, flame resistant and low smoke products. We always go for phenolic resin. Phenolic products have finding wider application at high temperature resistance, electric property wherever it is required, wear resistance and good chemical resistance. We always use phenolic resins. Phenolic resins are always used for making bulk products, bulk components. Now let us move to thermoplastic. So if you want to consolidate in thermoset non-recyclable, it will have predominantly it exists in a liquid form at room temperature. So it tries to help us in giving shape to the composite very easily, but it is non-recyclable. Till now, people have been exhaustively using lot of thermoset matrix polymer composite for various applications. Now, because of its non-recyclability, thermoplastics are getting pushed very hard by aerospace industry, automobile industry and marine industry for various applications. But what are the issues related with thermoplastic? Thermoplastic means you need to have, it exists predominantly, it exists in solid form. So in order to convert it into a liquid form, you need to apply very high temperature, and for pushing this, when you try to take it to a high temperature, that means to say around the glass transition temperature, it is viscous in nature. With this viscosity, if you want to make a composite, it is difficult. So we always apply pressure along with this temperature to get a composite out. So that is what is the restriction of thermoplastic. But the major advantage is it is recyclable. So with this, let us get into thermoplastic resin. Thermoplastic resin, what we will cover is nylon, polypropylene, polyethylene, tetraphenate, PET, which is used for exhaustively used for making water bottles, which is called as PET bottles. So then it is PEEK, polyethyl ether ketone. Then it is polyphenyl sulfonate, PPS. These are some of the most commonly used thermoplastic resins. So nylon are exhaustively used in the intake manifold. It is used as gears. In the printers we use nylon gears, wherein which it has low friction. It is used as bearing material, bushing, sprockets, etc. are made. As far as thermoplastic is concerned, you can't use long and continuous fibers for making composites. We always use short fibers. So it is easy to mix thermoplastic nylon with glass fillings, and directly you can try to use injection molding process to make a component out. Nylons are exhaustively used for making pultrusion components. Nylons are also called as polyamides. There are several types of nylons, including nylon 6, nylon 66, nylon 11, etc., each offering a variety of mechanical and physical properties. The next most common is polypropylene. So it is polyolefin are used by far the largest class of synthetic polymers made and used today. The attractive properties are it is low cost of production, lightweight and high chemical resistance. A wide range of mechanical properties is possible just by doing copolymerization, blending and additives. That means to say you keep adding ingredients such that the properties of the thermoplast can be changed to meet out your requirements. The densities are as less as 1 gram per centimeter cube. So if you talk about steel, it is 7.8. If you talk about aluminum, it's around about 3 to 4 kg per meter square. So here if you see it is around about 1. So it is very, very lightweight. So it can be used for several applications wherein which it is a moving body. For example, car, you can use it. And exhaustively today, polypropylene thermoplastic composites are used for lot of composite parts in automobiles. So it also has high stability towards oxidation, which tries to use this property for several applications. Next one is PET. PET is polyethylene tetraphthalate, is generally made out of dimethyl tetraphthalate and ethylene glycol. So these two mix together to form PET. PET has a melting point of 265. Because of its presence of aromatic ring, it is also highly crystalline and rigid in nature. So this can be used for high strength applications. This polymer is difficult to process due to the presence of large number of para-linked aromatic rings in the molecular chain. So processing it is slightly difficult because you need to have high temperature and pressure. A small amount of dimethyl isophthalate is introduced during the polymerization reaction, which reduces the crystallinity and rigidity by forming meta-linkage. So what are you trying to do? You are trying to play with the properties. Is one of the most common commercial polymer. It has very good chemical resistance to mechanical strength up to 175 degrees Celsius. It is not at room temperature, at high temperature. So this is what PET is also exhaustively used in process industry, especially food processing industry. Next is polyvinylene sulfide. So PPS molecule consists of a repetition unit of this figure. This is the unit cell. Okay, the crystallinity of this polymer is around about 85% and the melting point is around about 285 degrees Celsius. The flexible sulfonide linkages are responsible to lower the glass transition temperature. Why is glass transition temperature important? Because it is very clear. This is a temperature where you have to take the polymer and afterwards you process it to give a required shape and size. The flexibility and the simple structure of the molecules leads to a better crystallinity. It has an excellent chemical resistance and it can work up to 345 degrees Celsius. So you look at it, all the polymers what we have seen, each one, this works very good at room temperature, slightly higher, it is much higher, 175, then it can go up to 300 degrees Celsius. We have just listed it according to the temperature which it can be processed and which it can work. PEEK is a new generation thermoplastic that offers possible of using of high service temperature condition. The glass transition is 143, the crystalline melting temperature is around 336. It has the advantage of almost 10 times more 10 times lower water absorption than epoxy polymer. So it can be used for several marine applications. PEEK is exhaustively used because it does not absorb water. What happens if it absorbs water? There is a property called as hygroscopic. Water gets absorbed and the polymer gets swollen. So this is a very common feature in polymer matrix composite. If at all there is a defect, then or a crack, through this crack if a water enters inside, it tries to swell the polymer. So that kind of defects will not happen with respect to PEEK. The water absorption of PEEK is around about 0.5 at room temperature, whereas aerospace grade epoxies have 4 to 5% of water absorption. So look at it, the epoxy is a thermoset. Thermoset absorbs and it expands, but whereas PEEK has an absorption of 0.5%. And again, you should be now mentally be clear, it is not one property you choose and pick a polymer. You always look for multiple properties. Depending upon your requirement, you have to start using it. For example, in aerospace, we look at water absorption less, we look at smoke less, we should look at lightweight, we should look at slightly higher temperature. So all these properties are thought of, and then you choose a polymer for it. So with this, we will try to come to an end of the second lecture. The second lecture was predominantly focused on matrices, and in matrix we first saw what are the functions of a matrix, then we saw different types of polymer matrix. One is thermoplast, thermoset. Again in thermoset, some classifications of thermoset polymer matrix and some thermoplast polymer matrix composite. I am sure by this you will try to have a small feel that polymers can be classified, and they are classified according to the recyclability and how do we choose which property for making a composite or a product. So I will end this lecture with a small assignment. Again, this assignment is a home assignment, you don't have to submit it to me. You can choose any one thermoplastic product, it need not be a composite. Choose one thermoset product, a polymer, and then what you do is you list down all the properties, and when you list it down, you write the relative properties. That means to say lighter, heavier, stronger, weaker, ductile, brittle. Just write like that. So when you start listing down all the properties, keeping two polymers in your hand, then you try to understand the properties in a big way. So with this, we will try to come to an end for the lecture 2. We will meet in lecture 3, wherein which we talk about reinforcements. Thank you very much.